We are now ready to look at TCP versions. In this video, we will look at two such versions, Tahoe and Reno. Now, if you're wondering what are these names, where did they come from? Actually, these are famous gambling places, that is casino places in the US. I have no idea why TCP chose these names. Maybe because TCP gambles itself when it does congestion avoidance. But anyway, a few quick questions. To do congestion control, TCP relies on these three mechanisms. Slow start is about filling the pipe. RTT estimation about conservation, that is not putting a packet unless one is removed from the pipe. And congestion avoidance is about adapting to the path. So in this video, we will put them all together in different TCP versions and look at some concrete examples. TCP Tahoe is one of the initial versions of TCP. In fact, it's the simplest of the lot. So it basically employs go back N protocol, the sliding window protocol, with slow start and congestion avoidance. So it uses two variables, CWND you are already aware of. There is another variable it uses called SS thresh. Its role will become clear soon. At the beginning, it does slow start. So it starts with the congestion window size of 1, and for each new data that is act, it increments this congestion window by 1. Now, when you do this, you're bound to overestimate, leading to loss of data due to congestion. Suppose your window size is 25 packets. So you start with 1, you make it 2 after another round trip time. It becomes 4, 8, 16, and then 32. At this point, you are pushing the network into congestion, and congestion avoidance tells to cut the rate by half. Now your estimate is 16, and then you will slowly probe the network to see if you can increase this window size through that additive increase. Now tell me, the way you found out about the congestion is through a timeout event. So at the time of timeout, how many packets of yours are there as part of the network? In other words, are there any of your packets in the pipe? Well, the pipe is empty because timeout is often twice the round trip time. By this time, you have emptied out all the packets in the pipe. Now your estimate is 16. So what should you do? You can send 16 packets to fill up the pipe. Do you again just dump the 16 packets into the network? No, right? Because slow start's origins was to precisely avoid that. So to reach this value 16, you again have to do slow start. Many people find this aspect confusing. Slow start is different from congestion avoidance, but both of them control this congestion window size. So when should slow start run? When congestion avoidance should run? One has to be clear. So this explains it. So on timeout, you are going to invoke congestion avoidance, which basically is cutting your window size by half. So the 32 in the previous example was cut down to 16. So this is your CWND right now. This is the estimate of the capacity of the pipe. But then you don't want to dump these 16 packets that they go into the pipe, because as it is already congestion, and this will cause more congestion. So what you do is you have to do slow start to reach to this value. So for that, you store this 16 value, which is CWND by 2, into this variable called SS threshold. What this is saying is until you reach this value, you do slow start. After you hit this value, additively probe the network to see whether you can get some more. So that is what this is saying. When new data is act, I'll get to this point why new shortly. If the CWND is less than SS thresh, you do slow start. That is, you increment the congestion window by 1 for every acknowledgement you're getting. So what this translates to is, in this example, your estimate is 16, but you don't want to dump 16 packets in one go. So you start with 1, you go to 2, you go to 4, you go to 8, you hit 16. So this is the slow start phase which this is achieving. Now, once you hit 16, which is where you equal the SS thresh, after this point, you have to do congestion avoidance, which is the additive increase. So from this point on, you probe the network in this particular fashion till you hit the 25, which is the right value of congestion window in that specific example. And this additive increase, as I mentioned, is done based on the self-clocking mechanism, where for every ACK, you're going to increment the congestion window by this, whereas here for every ACK, you incremented the congestion window by a value of 1. So why new data? This should rather be obvious, because if you are getting a duplicate acknowledgement, you have no idea what is happening. When you get an acknowledgement for new data, this is what is telling that a packet has been removed from the pipe. A duplicate acknowledgement is not giving proper information. Well, in reality, a duplicate ACK also is telling that a packet has been removed from the pipe, but the TCP Tahoe version of it is not going to act on it. Later versions tackle this problem, but for now in TCP Tahoe, you are going to ignore these duplicate acknowledgements. So the same is captured via this figure. So to begin with, you do slow start, where you start with a congestion window size of 1 and increase it by 1 for every acknowledgement you get. So what this boils down to is you're doubling the congestion window every round trip time. So that is the exponential increase that you're seeing. And as you keep doing this, finally you're going to push the network into congestion, and that happens at this particular point. So then you're going to wait for a timeout. During this time, the pipe is drained. So as soon as you time out, you cut the congestion window by half. So this is your operating point. But to reach this operating point, you again start with a window size of 1, do slow start to get to this point. After this, you do congestion avoidance, where you slowly probe the network for additional bandwidth, where you increase the CWND by 1 every round trip time. Nothing like an example that explains all this. So let's look at a TCP Tahoe example. So here is an example of TCP Tahoe. What I'm about to draw will not be to scale. What is important is the sequence of events. In other words, what event is happening in response to what event. This example is a bit complicated. I have specifically chosen it to illustrate the various aspects of the protocol, so pay attention. TCP is a byte-oriented protocol. It works with bytes as sequence numbers, but for simplicity of explanation, I'm just going to use the sequence numbers to represent packets. So to begin with, you start with a CWND of 1, thereby you could transmit 1 packet. And now when an ACK for this comes, you increment the CWND by 1, which makes it 2. Thereby you can transmit 2 packets. And when the ACKs for this come, you increment CWND. In the process, during this phase, this round trip time, the CWND becomes 4. Thereby you can transmit 4 packets. And again for ACKs for this, you are again transmitting 8 packets. So this is the slow start phase, which we have already seen before, nothing interesting yet. So this last packet in here got lost due to congestion, and the sender still doesn't know about it. Now ACKs for this 7, 8, 9, 10 packets keep coming, and then again you're incrementing the CWND for each of these ACKs. So you increase from 15, 16, so on and so forth. Now tell me, what will this CWND value be? Well, it is not 16 because you did not get an ACK for 14. So this turns out to be 15. What will the sequence number of this last packet be then? Well, it will be 28 because you have received overall 7 acknowledgements. So you can send 14 packets. So they range from 15 till 28. Let's say among this bunch, again 26 and 28 got discarded because of congestion. Now all these packets that were received are going to send a cumulative acknowledgement. Since they did not receive 14, they are all going to ask for 14. Okay, this is what is being represented here. So I'm going to use this notation for the ACKs, where the number X here represents asking for, this receiver is asking for this packet. The Y here represents who generated this ACK. In other words, it received 15, thereby it is asking for 14. It received 16, thereby it is asking for 14, so on and so forth. The sender does not know about this value of Y. This is just being written here for understanding purposes. The sender only sees that it is receiving duplicate ACKs. So if you notice, these duplicate ACKs are indeed conveying information that likely this packet 14 is lost, but TCP Tahoe does not act on these duplicate ACKs. Since you're not acting on these duplicate acts, you have to timeout for this packet 14. That's what you do. So this is the timeout event. Once you timeout, you're going to retransmit this packet 14 and you're setting your congestion window to 1. And what will your SS thresh value be? Well, it is CWND over 2, but this has to be a proper packet number. So we'll take the floor of that. Thereby this is taken equal to 7. So when an ACK for 14 comes, this is represented here. What is this ACK going to ask for? 26, right? Because this packet 26 is lost. And in response to this, acknowledging this packet 14, you increase your congestion window by 1. Thereby it has become 2. Now what packets can you send in response to this? Remember, we are working with go back N. So because of this go back N operation, you are now going to start from fresh. So you start with 26 and you're going to send 27 also, even though it was successfully received at the receiver. The sender doesn't know. It just is going to start with a clean slate because of the go back N operation, and it is going to send these packets. What is this ACK generated in response to this 26 being received ask for? 28, right? Because that is also lost. And similarly, this 27 is also going to ask for 28. Now in response to this ACK, you set your congestion window to 3. So how many packets can you send and what are their sequence numbers? You can send 3 packets because this packet is acknowledging 27 also. So it is asking for 28. So there is nothing outstanding. So you can potentially send 28, 29, 30. Now in response to this particular acknowledgement, what will your CWND value be? Well, you will not increment the CWND value because this is a duplicate ACK. So nothing more to be sent as well. Now as the ACKs for these packets come, you're going to increment by 1. So that will make CWND equal to 4, 5, 6 because you're getting 3 acknowledgements. In response to this, you will send packets 31 to 36. When you receive an ACK generated by this particular packet 31, your CWND becomes 7. Thereby you hit the SS thresh. From this point on, you are going to do congestion avoidance. So as a consequence of this, what all packets can you transmit? You can transmit 2 more packets, which is 37 and 38. Why? Because this ACK is saying this is removed. There are 5 more as part of the pipe and your congestion window is 7, which means you can send 2 more. After this point, when you get acknowledgement for packet generated by 32 and acknowledgement for other packets, since you are in congestion avoidance, you are going to increase the congestion window by 1 over CWND. That is, when you get an acknowledgement for ACK generated as a consequence of packet 32, you are going to increment it in this fashion. And this incrementation will happen until you hit the value 8. Only then you are permitted to send another packet. So that's congestion avoidance. TCP Tahoe has some fundamental drawbacks. One, it is slow to recover from losses. For example, in this example, even though you're getting this duplicate ACK information that is telling that something could potentially have gone wrong, it is not acting on it. It is waiting for a timeout before it is retransmitting 14. So during this entire time, the link is idle. And not only that, these timeouts are going to drain the pipe, in which case one has to fill the pipe again through slow start, which takes time. So this is also shown here, where during this time you have drained out the pipe, and to reach this value of congestion window, again you have to spend some time to fill up the pipe. Both these drawbacks are handled by the next version of TCP called TCP Reno. So we will see more of this in another video. So let's break.